Hello everyone. This is group. Hello everyone. This is group 5. Our topic is differential equations. These are our group members. My name is Chen Mingyue. My matric number is 209426.
Hello everyone, my name is Tian Lin. My metric number is 209467.
Okay, I'm going to start by introducing linear differential equations and nonlinear differential equations, in which dependent variables and their derivative occurs as products reset to powers or in any other nonlinear functions. That's the property of nonlinear differential functions. And the linear differential equation of opposites of nonlinear differential equations. I have summed out their difference in 3 ways. Number 1, the coefficient before the derivative of y can contain y, but it can contain x. Number 2, the coefficient before y can't contain y, but it can contain x. Number 3, the only thing that happens in this whole equation is y, and the derivative of y, not saying y 2 power of y and 3 power of y. Here are some important examples, and we can classify them necessarily by 3 points. We just mentioned. That's all have to see.
Okay, this is my part. I'm going to explain the homogeneous DE versus non-homogeneous DE. There are some simple equations. Okay, there are 3 simple equations. Let me explain what is homogeneous DE. As you can see for the first equation, Fy over x. So this one, homogeneous means there are the independent variables. The number of independent variables are same, and the power is are also same. So for the second equation, 1 plus y over x, as you can see, there's 1 y and 1 x, and we consider this atom as 0. The third equation, f equal to ax squared plus bxy plus cy squared. As you can see, there's 1 x squared and also 1 y squared. And bxy, the xy is just 1. So this equation is a linear homogeneous PDE. It's more than 1 independent variables. Okay, next page. Homogeneous. There are the second method to find homogeneous DE. There are it is equation Fax equal to a to the power of k multiply fx. And in the same way, f zx zy equal to z to the power of n multiply fxy. Next page, please. Okay, the third method to find homogeneous equation, dy, as you can see, this equation dy over dx equal to x plus y over x minus y. we can change this equation to the up one. X plus y multiply dx plus y minus x multiply dy equal to 0. This method is same in the model 1. When the right hand, if we change the equation and the right hand is 0, it could be a homogeneous equation. Next page, please. And let me give some examples. The first example, the function fxy equal to x cubed as x squared plus y squared is homogeneous of degree 2 because fx fzx zy equals zx squared plus zy squared equal to z squared multiply x squared plus y squared equal to z squared multiply to fxy. When we multiply z with the independent variables of x and y, it doesn't change. It doesn't change fxy. We can put z square in the front. Okay. The next page, please. Example 2, the function fxy equal to square root x to the power of 8 minus 3 x to the power of 2 multiply y to the power of 6 is homogeneous of degree 4. Because if we multiply z to the x and y, square root zx power of 8 minus 3 zx to the power of 2 multiply zy to the power of 6, we get a z to the power of 8. As you can see, the front one is power of 8, and then the second item, we could get z to the power of 2 multiply z to the power of 6, which means it's also 8. We can put z to the power of 8 in the front, and we get it in the front, and finally we get z to the power of 4 fxy. So we put a z into the equation and it doesn't change. We can put it in front and it doesn't change the fxy. The next example. Example 3, the function fxy equal to 2x plus y is homogeneous of degree 1 because we put z, we multiply z with x and y, we get, we also get z multiply fxy. Okay, next example. Example 4, the function fxy equal to x to the power of 3 minus y to the power of 2 is not homogeneous because if we multiply z with x and y, we get zx to the power of 3 minus z multiply y to the power of 2. And we get the final result we get is z to the power of 3 multiply x to the power of 3 minus z to the power of 2 and multiply y to the power of 2. And we can't make the right hand to be 0, which does not equal to z to the power of n multiply fxy for any n. Okay, so it's not homogeneous. Next example, please. And this one is the function fxy equal to x to the power of 3 multiply sine y over x. It's homogeneous of degree 3 because we multiply z with xy, we get, we can put z in the front. Finally, we get z to the power of 3 multiply fxy. Okay, the fxy is still same, it's homogeneous. Okay, next example. A first order differential equation mxy multiply dx plus n xy dy equal to 0 is said to be homogeneous if mxy and nxy are both homogeneous functions of the same degree. Okay, the example 6, x squared minus y squared multiply dx plus xy dy equal 0 is homogeneous because both mxy equal x to the power of 2 minus y to the power of 2 and nxy equal to xy are homogeneous functions of the same degree. Okay, next page. Okay, my part is finished. Thank you.
I will be talking about the equation, so what is ODE? Basically,
Excuse me, Pedro, your voice is low. Can you make it louder? Very slow volume, very low volume.
Can you hear me now?
Yeah, it's very good now.
Okay. Sorry for the interruption. So I will be explaining about ODE vs PDE. ODE, when it is involved only one independent variable. For PDE, it is the opposite of ODE, which is it involves more than one variable. So here we have some example. We have d squared f over dx squared minus 4x df over dx equal to cos 2y. So this is an independent variable because it is only it only have x, but the other one is df over dx plus df over dy equal to 4x squared plus 2y. So this is independent variable because it has x and y variable. Next slide, please. Okay, when we talk about ODE and PDE, we normally use chain rule to convert an ODE into PDE. For example, when a function is defined by y equal to fx, where x equal to gt and y equal to ht, t is the parameter. So we have example here, dy over dx equal to dy over dt multiplied by dt over dx. So to convert the ODE, we can simply cancel out the dt, so we get dy over dx. Next slide, please. So this is the order of DE. The order of DE is defined by the degree of the highest. So for the first one, for the first example, we have d squared f over dx squared minus 4x df over ds equal to cos 2y. So this is the second order because the highest power is 2. So for the second one, df over dx plus df over dy equal to 4x squared plus 2y. So this is the first order of PDE because the highest order is 1. The x squared there is not included because it is not in the DE. So for the third one is we have dx over dt to the power of 3 plus 4 dx over dt equal to 0. So this is the first order because the x there is only the power of 1. So this is first order of the x. So I think that's all for our book. Thank you.
Thank you.